Okay, good afternoon to everyone. Welcome to this colloquium at the Physics and Astronomy Department of Padova. Before starting, of course, well, first of all, let me thank you for your presence here in person. It's, I think, the second colloquium that we have in person, and I think it will be a great success. So before starting, it's a pleasure for me to introduce the speaker today, Professor Benjamin Wandelt. A few words, just to sketch shortly, actually, what he is working on. So Professor Benjamin Wandelt got his PhD in astrophysics from Imperial College of London, and then he was a postdoc for 2 years in Copenhagen before actually moving to the Department of Physics at Princeton University until 2001. He then actually joined the faculty of the Astronomy and Physics Department at Illinois University at Urbana-Champaign. And then he moved to France in 2010, where actually he was awarded the International Chair of Theoretical Cosmology at Sorbonne University and at the Institut of Astrophysics in Paris. And there in 2014, he contributed to the establishment of a new research center, the Institut Lagrange in Paris. Actually, he became a director of this institute in 2014. And let me also mention that recently, in 2018, he joined also the Center for Computational Astrophysics at the Flatiron Institute in New York City. Professor Benjamin Wandelt actually is a renowned cosmologist. His main research work is cosmology, and actually his research activity ranges from theoretical cosmology, but in particular to computational, and actually also to astrophysics and cosmological data analysis, trying to really connect fundamental physics in cosmology to available astronomical and cosmological data, available from, for example, cosmic microwave background anisotropies and the large-scale galaxy surveys that we have at our disposal. He got various prestigious actually prizes in different actually countries. Just to mention a few, he got the Xerox Award and also the Frederick William Bessel Prize. And recently, in 2019, he was elected fellow of the International Association of the Astrostatisticians. Let me also remember that actually he co-led, together actually with Professor Matarrese here, the non-Gaussianity, the primordial non-Gaussianity analysis within the Planck satellite collaboration for the studies of Gaussian anisotropies. It is a real pleasure to have Professor Wandelt here today, and together with him, we will machine learning the universe today, trying to connect cosmological physics with artificial intelligence. Thank you.
Thank you very much, Nicola, for this very kind introduction. It's a special pleasure to be here today. It's actually the first in-person colloquium that I'm giving that as a visitor since 2 years, I guess, a little bit over 2 years. And it's a wonderful place to come and meet many dear colleagues, and I've enjoyed my visit very much so far. So without any further ado, let's get into it. Before I talk about artificial intelligence, I think I'll talk about real intelligence. If it will let me. There we go. This is the result of a lot of intelligence working of many people working for hundreds of years. and this is a remarkable compression of everything that we know about physics and that is experimentally confirmed into just 2 lines of mathematics. The accomplishments of Galileo Galilei are in there. Everything that has come afterwards, Einstein is in there. Oh, let me see if I think I have a pointer. So here's Einstein. Symmetry transformations, generalizing those of Galileo. So Lorentz invariants, Poincare invariants are encoded in here. Gravity, all force carriers, particles, and the masses of all known particles. So all of the laws of physics that you need to describe pretty much anything that happens in the universe is encoded in this very short bit of mathematics. So this is a remarkable feat of intelligence and compression of what we know of a lot of experimental facts and a lot of data into quantities that respect certain symmetries. That is really what physics is all about. And let me just warn you that artificial intelligence is still quite far away from being able to do things like that. So when I talk about artificial intelligence and machine learning in the context of cosmology, it's really a tool that helps us to to deal with the complexity that emerges from this quite simple description. There's a lot of complexity that emerges. All the known universe, all the phenomena in it, as far as we know, can be described by this, except for a few, and most of those phenomena that you don't find here have been discovered in astronomical contexts. So, for example, we know that the neutrinos have to have mass because of solar neutrinos. We know that there has to be dark matter because of astronomical observations, many different astronomical observations. We know that the universe is accelerating, and so that there has to we're not quite sure what does it, but one way to describe what we find in the data is by assuming a cosmological constant, which you could think of as a constant piece in this potential here, but tuned to a very, very strange value. So while we have all this known physics that represents all this integrated study and intelligence and this compression into extremely high value information, there's a lot that we don't know. And so far, at least for the last, I would say 20 years, cosmology has really been, and astronomy has been a portal into showing us that this is incomplete. There are also theoretical arguments to suggest that it's incomplete, but in terms of the observational evidence, that's been driven by astronomical advances. So, going to cosmology, since I'm going to be talking about cosmology, I thought I'd give you a lightning review of what cosmology is. And here you have all of cosmology on one slide. So this is an extremely important concept in cosmology, which is that this is our past light cone. So if we sit up here, so time here runs upwards on the slide, and space is condensed into just into horizontal planes. Okay, a moment in time is the space in a horizontal plane on this diagram. And the cone that I've drawn here corresponds to the place, corresponds to the locus in the space-time diagram of where light travels. Okay, so when you look out into the universe, what you actually see is the surface here of this cone. So light reaches you from very far away, travels on this cone and reaches you here today. So all the observations that we see using massless particles, so in particular photons, light, originated at some point in the past. So in some sense, when you look you don't really look in space, but you look in time. Actually, it's a combination of space and time. So looking out into the cosmos necessarily also means looking back in time. This is an important concept. And so time, as I said, is running upwards here. And the base of this cone represents some very, very early cosmic time, which I call the end of the beginning. So there is some process that prepares the universe that makes it large and long-lived and smooth and with some initial fluctuations. We have models for that. Inflationary model is one that you may have heard of, and probably the most popular, and with some support from observations. And but then from that moment on, the universe evolves, essentially using those laws of physics that are encoded in the previous slide. The universe starts in a very hot state where radiation dominates the energy budget of the universe, radiation pressure and density. And then as the universe expands, I haven't drawn the expansion on this diagram. I've actually divided out the expansion because that makes the diagram more complicated. But the universe expands as time goes on, and the radiation cools off because it's an expanding universe. And eventually there's a little bit of matter in the beginning that eventually begins to dominate the density budget of energy density budget of the universe. At some point, all the light that's still left over from all this radiation decouples from the ordinary matter in the universe. So this happens because charged particles combine into neutral atoms, and so but some of the light keeps streaming, and I'll show you this in more detail on the next slide. There's a period that we call the Dark Ages, because other than this primordial afterglow of the Big Bang, the cosmic microwave background, there is no other light in the universe until the first stars form. The first stars produce really the first new light in the universe. This happens here, and then in the relatively recent history, this was a big surprise when this was found about 20 years ago. It turns out the expansion of the universe that was actually getting slower with time, decelerating, suddenly started accelerating. And one way to describe that, or one physical model that does this, is called dark energy. And we have absolutely no idea what that is. All right, so big mysteries. On the left here, I've written down the various observables that lead us to this timeline. We look at surveys of galaxies and clusters of galaxies. We can model the distribution of gas in the universe, often through radio emission and absorption of the 21 centimeter fine structure, hyperfine structure line. Then there's gravitational bending of photons that travel past over densities or under densities. We have big lighthouses in the early universe that are extremely bright, quasars that are accreting and heating up matter so much that we see them across the universe. And we see how that light gets absorbed by gas along the line of sight. Then there's this cosmic microwave background, the afterglow of the Big Bang that gets released at some point in time here that we call recombination. And then there are aspects that we have not yet directly observed, like, for example, the slight spectral distortions in this cosmic microwave background that tell us about what happened before. There is a neutrino background. We're pretty sure it's there. It's been indirectly detected. So neutrinos from the Big Bang. But those neutrinos themselves today are very low energy and very difficult to observe, even though people are trying. And then there is also a background of primordial gravitational waves, if the inflationary model holds true, that we are hunting for but have not yet observed. Okay, so that's all of cosmology on one slide. And actually now I'll show you a movie of one cosmic microwave background photon as it travels along this light cone and reaches us. And so you see a lot of the events that I just mentioned playing out in this movie here. So let me actually skip through the beginning. Okay, so here's the photons are bouncing when the universe, before the universe recombined, bounce between protons and electrons. And I guess I should start my photon running. There we go. There's there is one of those photons, okay, at the surface of last scattering before recombination. And all right, so it starts traveling here on the surface of last scattering, on this past light cone. First structures form. Okay, stars light up, galaxies form. These galaxies clump together. Then these clumps of galaxies produce gravitational potentials, which lead to a deflection of this photon around these clumps. Sometimes these photons interact with charged particles that live in dense regions of hot gas and can change direction. And eventually, you see the photon gets redder and redder, so it cools down due to the expansion of the universe. So it starts off in the visible and eventually becomes microwaves until it is observed by our instruments once it comes to the Earth. Okay, so we'll go to the next slide. So what we want to learn from these photons and other photons that are emitted from galaxies that we see in our surveys are the big questions. The questions of cosmic beginning, question of cosmic content, and of cosmic fate. There are a bunch of parameters associated with each one, but what this really refers to are the initial conditions of the universe. How did the universe really begin? What happened? How did these initial conditions get laid down? How did these first slight perturbations grow into the structure of the universe that we observe? The dynamics of this growth tells us something about the content of the universe. And these parameters here, actually, as I go through, let me label all these parameters. So these parameters here describe the expansion, the acceleration of the expansion, the current expansion and the acceleration of the expansion, which we can think of as being driven by some dark form of energy. And so that's really about the expansion geometry, understanding how the recent universe began to accelerate. So we find here the density in matter, in ordinary matter like baryons, in neutrinos. So these are questions of cosmic content, how many stars formed at various times. These parameters here parameterize the statistics of the initial conditions of the universe. And these are dynamical parameters in terms of how the universe expands. Okay, so that's what we want to learn. So remember this, this past light cone here. If you look at the base of the light cone here, okay, this is a disk in this diagram. But if I expand that, remember I've suppressed some dimensions. So if I add the third dimension that I suppressed, the third spatial dimension, then this disk here at the bottom turns into a cube, into a ball, okay? And I've colored in this, this ball with a realization of what the initial curvature perturbation of the universe could have looked like. So this, you can see it's sort of correlated, okay? These correlations are scale-free correlations. Your world line, so this ball is centered on our past world line. So if you are here and now, and you draw a straight line down, then your world line is sitting there. And you can basically the world lines of any points on this ball are just going straight up on this diagram. And you can see, for example, that shells that are near the boundary of this ball, they will intersect your past light cone a long time ago. Okay, so these are relevant for the cosmic microwave background, okay, which gets emitted somewhere here on your past light cone, and shells that are more in the center here intersect your past light cone in the more recent past. And so that will determine the structure that we observe in galactic structure, for example, that we see closer to us, the distribution of galaxies in the local universe. I mean, when I say local, it's relatively speaking. I'm talking about distances that are much, much farther away, thousands of times farther away than the size of our galaxy, for example. Good to know that it's trying to do backups. All right. Okay, so I hope you now have enough background, cosmological background, to see where we're going with this. So here are these initial conditions of the universe, and a forward modeler will take such initial conditions, okay, and then together with these various parameters, so parameters of the initial conditions, parameters of the dynamics, and whatever instruments, you have to also model whatever instruments you use to observe, and then produce realizations of the entire observed universe. So the dark matter distribution, the cosmic microwave background, including galactic foregrounds, all the detailed observations that we take, and basically forward modeling that. Here's a picture of the galaxy distribution. And so this is what a physical cosmologist does, okay? Building models for the detailed evolution of the universe. And so we have universes in the computer, called simulations, that do this. And then the cosmological inference problem, so learning about the things here on the left from the observations on the right, is just turning that arrow around. So we want to take in these observations and then learn about the initial conditions, the beginning of the universe, and all the content and dynamics of the universe. That's the job of a cosmologist. And while, of course, there are many colloquia that could be given about many parts of this, today's colloquium is going to be about all of it. And it's really about a way to leverage recent advances in computational methods and in machine learning to try to attempt a new way of doing cosmology. And I try to explain to you what the old way is and what the new way could look like. So let me start with a simple example. Simple in inverted commas, because this was not simple at the time. I think it would be quite a lot simpler now. So the cosmic microwave background, of which I just showed you a map, has the structure imprinted in it and allows us to see the early structure, a processed version of the initial conditions of the universe. I told you these outer shells of the ball are relevant for this. One of the key features of the cosmic microwave background is that we can we observe the universe when the perturbations were small enough that we can use perturbation theory at high accuracy. And in fact, we only need to use linear perturbation theory. So all the equations that you derive from this big formula on the first slide, which are nonlinear equations, they all turn into linear equations, and that simplifies things enormously. Turns out that these coefficients that determine the structure in this map are just a linear operator, okay, which I parameterize here with these numbers, acting on phi of k. So phi of k parameterizes the picture on the ball that I've shown you, these initial conditions. So initial conditions acted on by a linear operator gives you what you see in the cosmic microwave background. And now we use symmetries. That's also a really important concept. Will remain important throughout the talk. We use symmetries such as we expect the universe to be, on average, the same independent from where we look. This is sometimes called the Copernican Principle, that our location in the universe is not somehow special, but that we wouldn't really be able to tell if we went to some other place in the universe statistically. and that directions in the universe are equivalent. Okay, that isn't a preferred direction. So under those symmetry assumptions, it turns out this 3-index thing here, which could be very complicated, actually it's more indices, right? L and M, 1 index each, and K is a vector, a 3 vector. So actually it's 5 indices. So that would be a horrible thing to have to describe. But it turns out it simplifies massively into this form here. So actually the M dependence is already fixed. The K dependence, the angular dependence is also fixed. So it's really just a function of two variables, and it only depends on the absolute value of K. Okay, it's much, much simpler. And the power of the CMB is that by observing the cosmic microwave background, you see the combination of initial conditions and physics acting in terms of this linear operator. So by exploiting that, you can then go to cosmological parameter constraints. For example, you see all the various parameters. I'm not going to go into the details. This is actually an old plot. Just to illustrate, we go to the cosmological parameter constraints that we get from Planck, for example. This tells you how much dark matter, how much dark energy there is in the universe according to the cosmic microwave background, and the lambda CDM model in which this is interpreted. Okay, now let me share with you a moment, a personal moment, which so this map here is actually a reconstruction. So as I said, here we have a linear operator, and as you know that we can try to invert linear operators. And so if you've ever taken any signal processing classes, you often have to deal with linear response functions, and there are simply ways to invert those linear operators with some regularization, which in this case is actually given by physics, turns out. So what I'm showing you here is based on the Planck data. Planck was a satellite experiment that was briefly visible there in the movie I showed you. This is the map of the Planck data, but processed through this inversion. So it's a reconstruction, actually, of one of the shells of this initial condition. And this is not the published version, but this is actually the one that I looked at the very first time when I did this to the data. That's why there's this weird bar across here, because there's some galactic contamination which was not cleaned out. And if you and this is really an image of the quantum fluctuations in the early universe that seeded the structure that we can access through the cosmic microwave background, through this reconstruction problem. And then combining temperature and polarization of the cosmic microwave background together adds more features. You get more resolution. And these are exactly the maps that we analyzed with several people here. Actually, there's a lot of people here represented that were very active in this analysis that formed the team. Michele Ligori, Nicola Bartolo, of course Savino as the fearless leader, which was at the basis of the Planck constraints on the very, very early universe. So, for example, put strong constraints on various early universe paradigms of how the universe was produced and how the structure was created. So this is extremely powerful. And this is just the simple thing we can do with the cosmic microwave background. Now, that is just one tiny little ring on that past light cone that I've shown you. And it turns out that you live in a very special time. Okay, this is actually the reason why I'm a cosmologist at the basis of it, is because I realized, it was well advised, and I realized now some time ago that we were living in a time, you still live in this time, where we discover the universe around us. Okay, just like there was a time when the explorers discovered the globe, okay, and then it was over. Then everything had been discovered. And now we live in the time where we discover the observable universe around us. And this will be over at some point. It's not going to take all that much longer. There may be a couple of decades still there, but at some point we'll have a pretty good picture of everything in the observable universe. And so it's a privileged time to do cosmology. And so this is, and we're filling in this past light cone exponentially fast. If you count the number of pixels or voxels that we're measuring, it actually follows an exponential distribution. And here's just a number of surveys, and I'm sure I've left out some very important ones that are ongoing or just finished or about to happen, that are doing this. Okay, and so what we want to do, what I want to sketch for you, is a way to kind of do what we did for the cosmic microwave background, but just for everything else, for the entire rest of the data set. How do we learn cosmology? This is what I mean by learning the universe. Okay, so underneath all of it, okay, and whenever you compare theory and experiment or theory and data, the tissue that connects the two is statistics. Okay. And if you don't like statistics, I fully sympathize with you. In fact, when I was a student, I hated statistics. So I've evolved since then. In fact, now I love it because statistics is this, I mean, as scientists, we somehow believe that we have privileged access. I mean, I think it's true, right? I mean, as scientists, we sort of deeply believe somehow that science is a special field of endeavor where we have some sort of privileged access to reality. And we have a way of grounding our theories through experiment. But the thing that makes it work, right, is statistics, right? The connection, the thing that tells us what we learn from experiment. Okay, so it's very important. And it's sort of, if you're a physicist and you don't like statistics, just think of it as information mechanics. Okay. In fact, a lot of quantum mechanics really feels like that. You're interrogating something, operators, information comes out. And it's basically the same thing, just a little bit different. Okay. All right, so how do you do cosmology, or really science in principle? Well, you write down a full physical and stochastic model of your data given a set of parameters. You then get the data. And so what I've written down here is sometimes called Bayes' theorem. So it's a way to learn from data. So this is the prior that specifies what you knew before you started taking data. This here is key in statistics. This is called the likelihood. So this tells you that what the distribution of the data is when you know exactly what your model is and you know all your model parameters. So this basically, if you draw from the D here, you're kind of simulating your model. You're running your model forward. And this thing here is the posterior, which tells you what you know about your parameters and your models, given the data that you've actually observed. Okay, so once you've actually observed data, you then you write this equation for the posterior, you stick the data in here, and you vary the parameters, and you see what you learn. Okay, so this is how to do science in principle. But most of cosmology has not actually been done this way. The cosmic microwave background analysis is probably the closest thing to doing it in kind of for real. That's right. How cosmology is actually done in practice, you pick some way of summarizing the data first. You don't take all of the data, you just count, for example, galaxies, or you compute two-point correlation functions. How many pairs as a function of distance, or triplets, how many, what triangle configurations happen, how often, and so forth. You then compute predictions for these summaries using your theory, often using perturbation theory, sometimes computers. And then you then write down an approximate likelihood for those, because you do need a likelihood, but you approximate it. So often you assume a Gaussian form, because that's the simplest. So there are multiple approximations involved here, and all of them carry risk. So the first one is, how do we know that these summaries that we chose to use, that they actually contain all of the information? They might not. In fact, most of them don't. The theory we use can be inadequate in some regimes. So I told you about perturbation theory for the cosmic microwave background. There it works really well. But as soon as you go to other regimes, you have nonlinear effects that are not well captured by perturbation theory. And in fact, over the last 40 years, people have pushed perturbation theory to the limit to try to model beyond the linear regime. But even then, you have to deal with all kinds of real effects in your data. The fact that there are real stars in the universe and black holes, and your instrument has systematics and all the rest of it. And then the fact that you're using Gaussian approximations at many places can lead to undesired side effects, indesirable side effects. For example, I don't know if you've heard about this, but there are now certain tensions people talk about in cosmology. Certain sets of measurements that don't seem to, or only barely seem to agree with other sets of measurements. And one of the questions, of course, that sort of is always just below the surface is perhaps these tensions. So when you talk about tensions, it really depends on the tails of probability distributions. So if you're assuming Gaussians everywhere, when really maybe the tails are much fatter and so forth, maybe some of these tensions are just artificial and the consequence of these approximations. Who knows? We have to go back and check that. But so let me first talk about what about that information that you might be missing. So here's essentially the closest thing we currently have to doing something with galaxy surveys that is similar to what I just showed you before on the cosmic microwave background. What if we could write down an explicit likelihood based on the observed galaxy survey, the full thing, not just in terms of summary statistics, but actually all the galaxy positions that you observe everywhere along the past light cone that I showed you, in terms of the initial conditions and cosmological parameters. So we've done this now for almost 10 years. We started with simplified versions before that, but this is the first paper that introduces this Borg algorithm. It's called Bayesian Oregon reconstruction from galaxies. And there we start with a prior for the initial conditions, which is also physics motivated. Then there's a model for gravity and the likelihood for so gravitational collapse of objects, and then galaxies somehow live in these gravitational clumps. And so we have all of these things built in at some level of approximation to this detailed forward model. Then all kinds of effects to do with the observations, the fact that you see part of the sky, you don't see infinitely far, and so forth. Then we explore the space of all possible initial conditions that could have led to that configuration of galaxies that you see in the sky, using a Markov chain method with many parameters, tens of millions. Without going into the details of how this works, but you're welcome to look at the papers, you take a survey, here's a slice through a galaxy survey, you stick it into this thing, and what comes out are possible initial conditions that could have given rise to your observations. And there's not one unique set, because the observations are partial. You see galaxies sparsely distributed in the sky, and you don't even observe the entire sky, for example. And in fact, because it has this physical model, it doesn't just give you the initial conditions, it gives you evolution histories for the universe. For every single possibility of the initial condition, it gives you a sample of those, a sample of possible true evolution histories. In fact, that's what posterior samples mean. Posterior samples from the posterior distribution give you possible versions of the truth given your data. So here's one such sample in a movie. So the movie here just goes through different possible configurations. These are the initial conditions that you're sampling over. Here are the data, they're fixed. This is an actual survey. This is the Sloan Digital Sky Survey main sample of galaxies. And what you see is that you're looking at all kinds of different initial conditions that put the galaxies in these places. And you see that where there's data, we're down here in this corner, where there's data, that you get a sort of fixed, let me run this again. Okay, so this structure is relatively fixed. All the filaments and all the rest of it are pinned in place by the data. Here, where there's no data, because we don't look there, you get all kinds of possible configurations, okay, that then connect to the rest of it here. So if you're interested in these kinds of methods and the current status of that, go to this website where there's a lot of information about this. So this does, in some sense, this kind of initial, here's the initial condition reconstruction, a small patch of it. It's a 3D problem, okay, but I'm only showing one slice. So this kind of does that. And in fact, because you have all the dynamical information, you can also predict things like what are the velocities of all those galaxies, which you don't necessarily observe. Right? And how did they get to where they, how did they start, how did they assemble, and so forth. So here, for example, is the Sloan Great Wall, which is a structure seen in the survey, sort of a large, seemingly coherent structure. And then you see here the fact, the blue and the red color in the radial velocity. So this shows that stuff here is moving onto the wall, you know, away from us here, towards us here. And it sort of shows you how the wall is still forming and growing, which you can use to do other things. Okay. So this Borg technique is currently the most advanced analysis where you write down an explicit likelihood and you sample it and you analyze galaxy surface this way. So is this the end of the story? Can I stop the colloquium now? No. It turns out that what we've discovered doing this is that the full statistical power in the data is enormous. And in fact, our model is not good enough, even though we have gravity in there and we have a way of saying how the galaxies relate to the underlying dark matter distribution. That's not good enough. Okay, now comes, so in some sense, Borg is sort of a very, very physics-based machine learning tool. Sort of it's actually a probabilistic inference engine for galaxy surveys. But it is too rigid, is what we've discovered. So a lot of things you can do with it, but if you want to do precision cosmology, the model is not flexible enough. So it overcomes the problem of having to choose summaries because you're actually analyzing the full data and therefore all possible summaries of it. But the likelihood we write down is too approximate. And turns out when we actually confront it with real data and we try to get cosmological parameters out, they don't really match up. And you know, it's clearly giving us things that are wrong at the level that we know from other sources, from simpler analyses. So the one idea then is to use machine learning to help connect physical models and data. Okay, so this gets us to the second point here, the fact that we have inadequate theory. So the simplified models, you know, this is, I mean, it's an achievement, technical achievement to be able to do this, and it's useful for many things, but it's clearly incomplete. Our model is not good enough yet. So how do we deal with the fact that our model isn't good enough yet? Well, I mean, you can just simply make the model more complex, okay? Put more effects in there, put more reality into the data model. Another way to deal with this is to have ways of cutting out parts of the data that you have difficulty modeling. So for example, let's say the smallest scales are particularly difficult. Well, then you might want to cut away the smallest scales, smooth the data, or add some noise on very small scales. Maybe the high density regions are difficult to model. So maybe you threshold those, or and all of these operations are actually very difficult to do using traditional techniques. And especially even combining them. And what's not allowed at all when you're doing statistics, I mean, basic statistics is you're not allowed to look at the data and then make decisions about how you're going to analyze the data, because they're a posteriori effects that could bias you. So nonlinear cuts based on the data are very difficult to justify in a statistical framework. But it turns out in this context here, actually, this relaxes it because, as you will see in a minute. And whatever you do, eventually there's always going to be some residual between your model predictions and the data. One thing I will show you now is an idea for how to learn that that residual using physical principles. So this is something could be called neural physical engines. The idea is to model the way, so bias is a cosmologist's jargon for saying how do galaxies relate to the underlying dark matter distribution. That's what bias means. It's short, that's why everybody uses it. It's nothing to do with statistical bias, biased estimator, things like that. It's a different concept. So, we designed a new type of neural network that can learn cosmological physics on small scales. And basically, we put it into Borg to translate between the dark matter distribution and the distribution of observed objects. In order to be able to do that, we can't use like DAL-E or one of these big machine learning models with hundreds of billions of parameters, because we actually want to learn those parameters from one data set. Okay? So it's not like we don't train it on the entire corpus of the internet, which is what people usually do in machine learning. So you see, actually machine learning and deep learning in the context of cosmology is often has a very different flavor because we're dealing with only one universe. And we have to take into account that we actually have good physical models to work with. So it turns out we write down, by including some physics symmetries and constraints, we can write down a neural network with only 17 parameters. Okay, I'm not forgetting the million or the billion. It's really 17 parameters. And this maps between the dark matter and the thing we're actually putting in, the data. And this gives you zero-shot learning. So in other words, this is a neural network we don't train, but the network learns the relationship between our model and the data. But because it's so heavily constrained, it doesn't destroy all the information, constrained by these symmetries. Okay, so here's an example of that running. So if you take, here's the simulated data. This is the initial reconstruction. Okay, this is at the final state of the reconstruction, not the initial density, but this is the reconstruction. And this is what happens when the neural network acts on this to try to match the data. So you see initially, it's now starting to pick up, this is as we're exploring the parameter space of these 17 parameters together with all the initial condition parameters here. The dark matter distribution, which is the evolved initial condition. All right, so eventually it manages to figure out the map between here and there, and then the information propagates back to the initial conditions, and you start getting the dark matter distribution, and this starts looking more and more like the actual data. So the network is learning the translation, and because we're building it into a physical model, it's constrained enough that it can learn both the translation and the dynamical structure and the initial conditions at the same time. Okay, now it has a fairly high contrast. Okay. So this is one possible approach to dealing with this problem. And this remains to be explored. This was an early test, and we're going to go further with this. Okay, now let's talk about the final one, the inadequate statistical approximations. All right, so I already told you how to do science using statistics, but the difficulty is that when you can't even write down this likelihood, because your data are so complicated. Galaxy distribution, the light coming from the sky. So you can't write down the likelihood. What do you do then? If you don't want to write down some simple approximation. So to get further, we need more freedom than just this traditional likelihood approach, which we're using in Borg as well. We're actually writing an explicit likelihood. After the evolution, you still have to decide how many galaxies are in this voxel, given that what the dark matter distribution looks like. And these assumptions are the root of why this isn't working so well. Not sufficiently well. It works quite well, but not sufficiently well. So we need freedom. We want the freedom to make our physical model anything we want, okay? We want the freedom to project, cut, summarize, mask our data in any way we want so that we can make contact with our imperfect models. And in order to do this, simulating data is often much easier than deriving the actual form of an accurate likelihood, okay? Because in the simulation code, you can simply change a single line and rerun your code. Whereas if you want to implement a new analysis with a new likelihood, it involves 5 years of work, a very significant amount of work. So the question is, can we analyze data if all we can do is simulate it, but we don't actually have this form for the likelihood? So it turns out there's a set of techniques that aims at doing that, and they're often called likelihood-free or simulation-based inference techniques. This is when the likelihood form is unknown or intractable. Sometimes likelihoods are computationally so difficult to evaluate that it's basically pointless to write them down, even if they could be written down. And I like to call these kinds of techniques in the category implicit likelihood inference. But I sometimes will use likelihood-free or simulation-based because those are the traditional names. So as opposed to explicit when you actually have to write it down. And this has been used in cosmology for some time, but this group of people here has been key in advancing the state of the field. And this relies on the following really basic insight, which is that data, when you simulate data given a set of parameters, what you're doing is you're drawing from the likelihood. Okay, so you can implicitly define the likelihood by these draws. So rather than writing it down, you can just say whatever my simulation code produces are draws from the likelihood. And that implicitly defines what the likelihood is. So here's how you would then do inference this is for conceptual reasons to show you that it's even in principle possible. This is not how we actually do it in practice. I'll get to that later. But so you write down your prior and you draw a set of possible parameters from the prior. Okay, the prior defines things that are physically possible. You draw your parameters. You have your data here. You draw parameters. You simulate forward. Okay, you extract something from these simulations that are your simulated data. And then you check, are those simulated data equal to the observed data? Okay. If they are the same, then you accept those parameters that led to them. And if they're not the same, then you throw the run away and you start again, you try again. Okay, so you only accept those draws from the prior that when you forward simulate, give you exactly your data set. And then, in that case, when you do that, then the retained parameters are draws from the posterior distribution. Okay, so this is how you can sample from the posterior. Now, it's an extremely wasteful way of actually doing it, but conceptually, hopefully, it's clear. This is consistent with what I said before. Draws from the posterior are like possible versions of the truth. Okay, so if the truth can generate the data, then it's a possible parameter. Okay, so but not otherwise. And because this is so wasteful, even if you have 5 numbers and they're real numbers, it will never actually get the exact set of numbers that you have in your data set. And so you often then define some distance between the simulated data and the true data, and you accept everything within some epsilon. So if the epsilon is not 0, you lose some information, but at least it gives you a non-zero set. Okay. So there's a problem that even if you define this epsilon, as long as you have more than one number, and your data is more than 1, 2, 3 numbers, the difficulty of actually hitting the true data with your simulated data becomes exponentially hard as the dimension of the data vector goes up. Okay, so it's an exponential. It's the curse of dimensionality. Hits you right in the face. And so, but it turns out that by compressing the data into informative summaries, by reducing the size of the data set. So let's see, you have your n parameters, you have your simulations, you extract all kinds of information from that. You can then compress that down to a set of numbers, and you can prove that you only ever need as many numbers, compressed numbers, as you needed parameters to capture all the information of the data set about these parameters. Okay, this is just from asymptotic statistics results. This is the Cramer, the information inequality or Cramer-Rao theorem, for example. Okay, so that means you can, if you have 5 parameters, 10 parameters, you can always do the problem in a 5 or 10 dimensional space, and that's much easier than dealing with a 1,000,000 dimensional space. Much, much easier. Okay, how do you explore the parameter space then? Still, you have to somehow deal with, still this accept reject method that I told you is still hard, even in 5 dimensions. And so this is kind of the scheme for this. here's the simulation pipeline I just mentioned. You draw from the prior some parameters. You generate your data, the simulated data. You then compress that in the same way that you compress the true data. And then you compare the data summaries and the simulation summaries in this magic box called likelihood-free inference, which then gives you the posterior probability. And so what's in this magic box? It turns out you can actually basically parameterize a very, very broad family of distributions using neural networks, so using machine learning techniques, so machine learning to the rescue here. It turns out by taking these simulated data sets and the true data set and their compressed versions, you can, by just looking at enough simulations, you can learn the either the likelihood or directly the posterior from observing enough simulations. And this is a set of papers that we're doing this. If you don't like if you have for some reason don't like Bayesian statistics, you don't have to be a Bayesian. You can also just directly learn the likelihood and do frequentist likelihood ratio estimation, for example. Okay, so this assumes that you have summaries that contain all the information. But remember, we talked about the risk. Maybe your summaries don't contain all the information. So how do you find the right ones? It turns out if you know the likelihood, you also know how to find the right informative summaries. But we already said we want to do this when we don't know the likelihood, where you can't write it down. So it turns out you can actually find optimal summaries also just from simulations. Okay. So here the idea is that because you have an implicitly defined likelihood through these forward simulations, you can fit this likelihood, as I said, using these neural density models. The compression works like this. You take a data set, you run it through a neural network, that produces your summaries, and then you compute a quantity which is the so-called Fisher information, and you maximize the information content of the summaries as the objective for training this network on the simulations. And this is described in this paper here. And we call these networks information, very creatively, information maximizing neural networks, or IMNN. Okay, so you can prove that in general, these networks will give you information optimal summaries of your data. So here's an example for how to use this. And now we're solving this a similar problem to what I was showing you with Borg, but now with no reference to the actual likelihood. It's not written down anywhere. So this is kind of doing the CMB analogous case. So it's a Gaussian random field, and it turns out you can get the parameters of that just by compressing this into two numbers, okay, and then looking at the distribution of that as a function of the parameters. You can, in this case, we know exactly how much information there is in the data, and you can see as you train the neural network, the information goes up and saturates exactly the bound that the theorem tells you. And this takes 11 minutes on one GPU, so it's not computationally intensive. I should tell you, these Borg runs I showed you before take much longer than that. They run on multiple cores for weeks to generate lots of samples. Okay, here's a non-Gaussian case. Okay, these are examples of cosmological density field slices. And same thing, you can train an information maximizing neural network, run it through this density estimation likelihood-free inference. So this field gets compressed into two numbers that saturate the information inequality according to the network. And then you do the inference, and you see for 4 different realizations here. These are the posteriors that come out, and the truth is in these crosshairs. If you want to actually do this yourself, you can. All you have to do is go to this link, and there's a Google Colab notebook that takes you through this exercise, and you can actually try this. You can it provides a trained information maximizing neural network for this particular case. And then you do the likelihood-free inference using that. And this is published. These plots are by Lucas Mackinnon, who was a master's student when he did this work. All right. There are other generalizations of this now, where we analyze. So this doesn't just apply to galaxy distribution. This works for 21 centimeter light cones. So this is absorption features from gas in the early universe, hydrogen gas. So you can take these, again, patches on the light cone and analyze them. But let me just get on to even more crazy applications of likelihood-free inference or implicit likelihood inference. So this, you can see this already, now we're talking about gas, and I just want to step towards analyzing full hydro simulations. So these are simulations that take supercomputers to run. They include not just the dark matter, they include gas, they include star formation, they include black holes and the way they interact and the way they affect galaxy formation. They include all kinds of physical effects. And because the whole point for building all of this is because we want to increase the realism of our models. And so let me show you where this is right now. So there's this collaboration called CAMELS that we are part of. And this generates large suites of full cosmological hydro simulations with multiple codes, which are, by the way, available. So if you want to play with these, you can download them. So we're making all the data available online. It's already online. And the motivation for this was to use these to train machine learning methods such as implicit likelihood methods. So here's an example. Here's what these data sets look like for all kinds of cosmological parameter combinations. I'm showing you all kinds of outputs here. I'll go through what these outputs are, but they include like star, stellar mass, per voxel, gas density, and so forth. And there are actually now more. There are 4,000 simulations for every set of parameters. That's not true. I'm sorry. There are 4,000 simulations for multiple parameter sets. So each one has one parameter set, and there are additional simulations all at the same parameter set. And so there's sort of various combinations of data, and you can download the data here. So this is led by Paco Villar-Escucha Navarro and Shai Genel at the and Daniel Angles Alcazar at the Simons Foundation, and multiple university affiliations. So here the hydro quantities are being simulated. You go down the list, metallicity, so this creation of elements in stars and so forth. Combinations of ratios of element abundances. And then there's also an n-body, just the run without all the gas and so forth, just the dark matter. What we're trying to learn is what cosmological information do these potentially observable things contain? So how do we analyze this? So it turns out here we're going to a slightly different method that sort of skips over some of the niceties and does a little bit more brute force artificial intelligence. So we're losing a little bit of AI safety now, but this scales to larger numbers of parameters, for example. Basically, you give up the idea of reconstructing the entire posterior density with all of the couplings between all the different parameters. You simply ask, where is the posterior located for each parameter, the marginal posterior, and how wide is the posterior? Okay, it's just getting a number and an error bar. And we call these moment networks. The idea is to basically construct two maps that go directly from the data. You stick the data in and it immediately spits out properties of the posterior distribution. So the thing I will be using next are called moment networks, or we call them moment networks. This is the paper where we described this, which was presented at a NeurOps workshop. So this is a machine learning workshop. And so by turning the inference problem into an optimization problem, trained by samples from the joint distribution of data and model and parameters. So this is where Bayesian statistics comes into this for these, because we're doing this integral by Monte Carlo sampling from the examples. And then these losses here are written down in such a way you can prove that these losses give you the posterior mean as a function of the data and the posterior variance as a function of the data. So we just find these functions of the data, and once we've trained them, then they instantaneously give us the result of the analysis. If you don't want to just have the location and the width, it turns out you can generalize this principle for to find maps that give you, given a data set, immediately spit out like the 1D marginals for the posterior. So for every parameter independent or for combinations of one or two parameters. And the reason why this is powerful is because it solves this curse of dimensionality, because you don't try to map out the joint posterior in large numbers of dimension, but you sort of go, you go directly to these low dimensional representations, which is what most people use, the only thing most people use in any case, in most situations. So here's the result. So here's this loss that I just showed you with a log added to it. Here are the cosmological parameters, matter density, amount of structure in the universe. Here are the astrophysical parameters. And this uses the gas temperature output of the hydro simulation. And you can see we can reconstruct cosmology very well from, so look, estimates and error bars. These are the posterior means and variances from the gas temperature, okay? With a very complicated physical model behind this. Here, just because we could, this is what happens when you do gas metallicity. So how many elements beyond hydrogen and helium were created? There's a lot of cosmological information in there, and it manages to kind of correct for all the physical processing, nonlinear physical processing that has happened. And so these are now artificial intelligence engines that we've built, and we can ask them questions. And so one thing we ask them is there still cosmological information when we look inside galaxies, for example, right? Because you can imagine maybe only the large scale has information about the whole universe. And we find that no, actually, all the way down to galactic scales, there is information. If we delete that, the constraints get weaker. One thing that was surprising is that even if we kind of, it's not very realistic because we can't really see the dark matter directly, but if we train this on the dark matter alone, which you think is kind of the pure thing that contains the cosmological information, it actually finds less information in the dark matter than if you give it all of those hydrodynamic outputs that are in principle observable. And I don't want to take time now because I think I'm starting to run late. So, the reasons for understanding why that might happen, but we didn't expect this when we went into this. And it turns out that there are some combinations of the data that are robust to the baryonic physics. So let me skip over that, but you see, actually, so we're doing this with multiple codes, train on one code, apply to the other, and you see that the physics are quite different. This is the gas temperature in two different codes, and yet certain measures seem to be robust to those uncertainties in the model. Okay, how much time do I have? Or I'm already over.
I think
you can finish up. Okay, so I have a few more minutes. All right. No, a few more minutes. Yeah. Okay. Okay, so one thing that we'll have to deal with in this context is that clearly, if you were doing simulation-based inference, so this implicit likelihood inference, where the likelihood is defined through the simulations, we'll need a whole lot of simulations. And so in the past we were limited by people time, but when you're using machines to do complex tasks, then you need a lot of machine time. Okay, and so this will, at some point, will become the limiting factor. How will we produce all the simulations that we need for this? So I told you that those were thousands of simulations. In other cases, that's roughly the order I expect we'll need to do this work. In fact, I mean, I'm cheating slightly probably because these models I showed you were trained on slices. Okay, they were trained on two-dimensional slices. It may be that we need a lot more simulations if we actually want to train this on three-dimensional volumes. but we haven't gotten there yet. There's some technical limitations that stop us for the moment. All right, so here are ways of doing what you need to do with less simulations. And this is actually a technique that works very generally, and we hope it will help us do this work. This is work I've done with my student Nicolas Chartier. And the idea is to, it turns out you can leverage, if you have approximate models available, you can leverage these approximate models to reduce the number of simulations. And you can, in a way that you can prove, will not introduce any bias, any error in your analysis. So here, for example, is a quantity of this is the dark matter power spectrum for the aficionados, and you see the red error bars are the estimate based on 500 simulations, full simulations, quite costly. And then underneath here, I show the blue error bars, which are much smaller on large scales, are about the same on small scales, which use only 5 simulations, but leverage the availability of an approximate code that is has a strong error, gives you the wrong shape, but it turns out you can combine it together and kind of get a speed up of at least a factor of 100 and even more on large scales. This exploits the fact that we actually have pretty good physical models. We understand this is physics after all. We want to use the physics and not just farm everything out to purely numerical simulations. This cannot just be used to estimate the expectations, to take expectation values, but also to compute covariance matrices. So if you want to, if you need covariance matrices from a small number of simulations, as you do in many cases, this is also possible. And there's now a Bayesian version of this, which just got onto the archive on Friday. So this is a method for using, you might have heard this, so this is actually a classical statistical method, the origin of it, called I keep blanking on the name of it. That's why we invented carpool, because it's much easier to remember. So it's basically the idea of finding covariance where you can subtract off the scatter from your estimates. It's a variance reduction technique. And this is a Bayesian generalization that also works for the covariance when you have simulations and fast approximations available. Okay, so you can use this for other things. For example, if you already have a whole bunch of full simulations, run at one set of parameters, but you actually want simulations at a slightly different set of parameters, you can use the ones you already have as your approximation and actually just run a few more to kind of transport the results to a new set of parameters. This opens up a whole bunch of possibilities. Here's another approach to reduce the number of simulations. Again, using moment networks. And by the way, now these moment networks here, in these moment networks, every single pixel is a parameter. So this is now a moment network with 65,000 parameters, 256 squared parameters. It's just to show you that this actually works also in high numbers of dimension, high dimensional cases. And so you might expect to need a lot of simulations for such a high dimensional case. In fact, the moment network was trained with a single image, which was based on a complicated magnetohydrodynamic simulation. The problem we're treating here is polarization foregrounds due to galactic dust when you want to look at the polarization of the cosmic microwave background. This is the search for primordial gravitational waves, which leave this imprint here on the cosmic microwave background polarization. Data might look more like this. So you see nothing of the signal because the foregrounds, this filamentary structure from galactic dust foregrounds is so large. And by training these moment networks, they return to you the posterior mean in every one of those pixels. So you can see you get a cleaned version of this image. And it tells you the uncertainty in every pixel as well. And you notice, for example, that in the high foreground regions, you also see high variance. This is not at all what you would get, let's say, with standard techniques. This uses something called wavelet phase harmonics. to basically take a single simulation and then reproduce lots of images that have similar morphological characteristics without running any further simulations. Okay. And it works very well. It's just a plot to show that these means and variances actually are correct. Here's a way to simulate the entire universe in a much more granular, much quicker way. This is a method that takes simulations that are strongly coupled across, due to long-range forces, and actually uses perturbation theory to split them into lots of independent, completely independent little volumes that it could, in principle, run on your smartphones. So you don't need large computers anymore to contain the full simulation. Then we can, the other thing we're doing is we're actually running a lot of simulations and putting them online for everybody to use. So you don't have to, not everybody has to run their own simulations. This is the largest release of M-body simulation data that's happened. It's about a petabyte of data, and more coming as we're running more, described in this paper. And then we actually also use machine learning itself to help satisfy our data generation needs. So here is an example where we take a low resolution N-body simulation, okay, going from the initial conditions. You now know very well what that is, I hope. At least you take that away from this talk. The initial conditions of the universe, run an N-body gravitational simulation forward to get a low resolution field. This is what you would have gotten if you had run a high resolution simulation, but we can train neural networks to take the low resolution and fill in the details. And you can see that there's a very close correspondence between those two. So we can upgrade. So we only have to store low resolution simulations, and actually we can super resolve. This is a technique that is now also used in the context of image generation, text to image, which I'm sure you've all seen, produces surprising results. Basically, these images are often generated at low resolution and then super resolved by neural networks. Okay, and this brings me to the end of my talk. So let me leave you with these final thoughts. We're in a regime where cosmology, we're still getting exponentially more data, but even right now, what we know about the universe is no longer limited just by the availability of data, but by the adequacy of our models and our analysis. And this is where machine learning and artificial intelligence can help us, because it's a very powerful tool that can help us solve cosmological inference problems. And often it can do that by recasting physics questions as optimization problems. And so, training a neural network, for example, or training machine learning algorithms, we found is a very efficient way of solving certain kinds of optimization problems. Now, artificial intelligence cannot do it alone. As you've seen on the first slide, real intelligence is still required. We do our best. But we have physics on our side. So this is a difference between applications of machine learning in physics and cosmology from maybe other aspects of science and academia or human knowledge or applications, which is that we actually often have physical models. You can just use the machine learning as a tool to really let the models play their full role in the analysis. And we want to combine physics insights with machine learning. So just, don't just download some tool and run it on data. Think about it, use the symmetries, use the things that you've learned as physicists that make you powerful thinkers when you analyze this, because the use of symmetry, the use of physical principles will give you massive benefits in this context. And well, yes, with great power comes great responsibility. Let's use it for good. Thank you.
Thank you very much, Ben, for this very interesting colloquium. And so it's time for questions, both here, and I remind also the people who are following the colloquium through the webinar that they can ask questions by raising their hands or through the question and answer option.
Okay, can you hear me now?
Yes.
Okay, well, thanks for the so I think I'd like to about the 15 slides maybe, and we were writing about the information content of dark matter density.
Yes.
Can you comment more?
The lensing story, yes. So when we train these methods on hydrosimulations, we have multiple codes. So the paper I referred to there looks at two different frameworks for doing hydrosimulations. They differ in how they simulate the gas dynamics. They make different assumptions about the physical models, for example, of how black holes accrete material and how they spew out the winds that come out of black holes, accreting black holes, that all the interactions that happen really on scales that are not resolved in the simulation. They're models basically about what happens inside every single little zone in the simulation, and and those different assumptions give you different results, as I showed in this here, right? And so if you're training on gas temperature using the illustrious TNG set of simulations and the SIMBA simulations, and then you apply them to the same kinds of simulations from the same code, you get very good results. But if you cross-apply them to the other code, you get results that are not correct, that are biased. And so this is what we're interested in, that because the difference between these simulations comes from really a lack of knowledge about what exactly are the most important effects. And so the real universe may not correspond to the left simulation or the right simulation, but something else as well. But one way we can test the sensitivity of cosmological analyses to assumptions about the astrophysical processes is by training a network on one simulation and then apply it on the other. What we found is that when we look, so as I said, we get biased results when we look at a number of different observables, but one thing that seems to be robust to this cross analysis is the total matter density. So if you take all the matter, the dark matter, the gas, the stars, the black holes, take all of that and we project that into a sheet, then analyzing that, training on one simulation and analyzing the other actually gives unbiased results. And that is good news, because that is exactly what you see in gravitational lensing experiments. So when you observe the light from background galaxies, as it passes through the large-scale structure, the light gets, changes direction, is lensed, and we can use that effect to reconstruct the mass distribution, and it tells us something about the clustering and therefore the cosmological parameters, like the mass density and the amount of structure in the universe. And part of the motivation for pursuing that is that we thought that should be more robust to the details of how galaxies form. And here we at least get some more evidence that that really seems to be the case. Right, I skipped over this plot. This plot shows that. So on the left, you see the case where, like, the blue points at the top, we train on one set of simulations and then apply it to the other set. And what's shown is the difference between the truth. So you see maybe a slight, it's a little bit high for low values of the parameters, slightly low for high values of the parameters, but it's doing fairly well sort of within the error bars. And the one on the right is for different parameters. So there it works, it's very consistent.
What's the one? Thank you for the I have a question. Information maximizing capabilities.
Yes.
I played with the notebook that you shared.
Yes.
I was curious, you trained the model with slices, so with 2D fields, and I was curious how this can be extended to 3D surveys, for example, and so also we include redshift-dependent parameter, for example, Galaxy survey analysis, age-dependent on Z, how can you use this in a 3D survey, and if you can use as a simulator, for example, last version, first simulation.
Yeah, right. It's a very good question. So it turns out, and I said this because this is in the interest of full transparency, because it turns out that in many, not all, I mean, I've shown you, for example, the super resolution work that was really in 3D, but a lot of machine learning papers in this field, when you look at them, and especially when they're working at the field level, actually work on 2D slices, and this has something to do with the fact that when you want to work with high resolution 3D objects and the whole neural network that goes with it, the current GPUs don't allow you to store all that information on a single GPU. So then you have to do the work of distributing this over multiple GPUs, and that is just a technological limitation. So either NVIDIA is just going to make GPUs with a lot more memory soon, or we actually did some. So we're in the process of actually generalizing this so we can run on multiple GPUs. That is one answer. Another possible answer is to represent the data in a different way, rather than representing it as there's a 3D volume. You can choose to represent it in a different way, as tabular data and other ways. So the question of how you embed the data and how you show it to the neural network is a key question that has repercussions with feasibility, how much information is involved. So there's potential ways of going beyond this limitation, and that representation question also addresses your other question about the redshift space dependence. So the fact that when you're looking along the light cone, because the way you observe the galaxies, the way you place them on the light cone is by measuring how much their light has been redshifted. That is affected by the radial velocities of the galaxies. And so there's distortions in the picture that come due to the dynamics of the galaxies that are due to that. And so that direction along the light cone is actually a little bit different from the direction across. And so again, that could be taken into account in the data structure. And so, that we're looking at those questions right now.
Other questions?
We've kept them for long enough.
Sorry.
We've kept them for long enough.
Yes. From home, Sarah. Okay. Okay, there's a question there.
Hey, Ben. A stupid question, but if you have two types of catalogs, on one of these, you have a system. You are able to know which one you have a systematic, and you are able to parameterize the systematic in the data. This extra degree of freedom, because this is crucial also for when you are making similar analysis for different traces, and somewhere there is a systematic, and which one is the product?
Yeah, we're not quite there yet where neural networks tell us what part of the data, what are systematics and what's not. But it is true. So those kinds of questions you can often address by looking for symmetries or some properties that you expect the data to have. And if the data violate those properties, then you know that there's some extra effect that's doing that. So there are a lot of those symmetries that derive from the average homogeneity and isotropy of the universe. That can sometimes be used to discover systematics. You can also train your model to recognize members, let's say you have your simulations, you simulate systematics-free data, you can train your neural networks, for example, to try to recognize such models. But that's kind of a trivial exercise, because almost certainly when you show that thing real data, it will say, oh, this doesn't look exactly like what came out of the simulations. So then it's a question of degree. And this is a general problem with anomaly detection in this context, because if you show real data to a network like this, it will almost always think that the data are anomalous, because there's some little aspect that isn't exactly the same as what was in the simulations. But we're not quite there yet, where we can train neural networks to say, oh, this data has these systematics effects, and this is how you deal with them. It's really an invitation for physicists to, for us to do our jobs and actually model the data at high precision. But these methods allow us to do that, and also to understand our data in such a way that we know what pieces to cut away, because we don't know exactly what the details are, so that we can make the correspondence.
Or extract new physics.
And of course, when there is reason to believe that it's real physics, but you know how complicated these things are, right? I mean, unfortunately, it's true that most amazing discoveries are wrong, right? Another way of saying that is that extraordinary claims require extraordinary evidence. So the first suspicion you should always have when you see a new result that is radically different from what we already know is that there could be some systematic effects, right? Yeah. So I mean, we all remember various great unexplained anomalies that went away. But yes, it's obviously important to find them, but then you have to understand them. And that work of understanding, at least so far, has not been taken away from us by artificial intelligence. But these methods free us really to be physicists and to think more about the forward models and make those realistic.
So given that comment, usually our old traditional techniques, we kind of knew where the information was coming from in the data. How are we going to know whether the things we discover are mistakes or real?
Right. Yeah, this is something we're grappling with. The question, for example, what if such an analysis here really finds some amazing result? For example, in the characterization of dark energy, if we found that dark energy doesn't behave exactly like a cosmological constant, that would be a groundbreaking discovery, because it would send a lot of string theorists back to the drawing board. So actually, well, sorry, if we found that it is very close to a cosmological constant, if we discovered it's not a cosmological constant, it would also be an important discovery, because we've now learned something about dark energy. So let's say we find this, how do we convince everybody that it's true? Or how do we interrogate this? How do we check this? So I've given a partial answer, for example, in the analysis of these hydro simulations. One thing we can do is we can delete kinds of certain information, or delete certain bits of the data and see how the result responds. So, for example, if you want to know, is the result driven by small scales, well, then we can filter the data or add noise and see how that affects the analysis. Is it driven by the high density regions, by the low density regions? Okay, you can take those bits of the data out, and in principle, you just have to rerun the analysis, because it's so flexible that it can easily adapt to new data model. Other things you can do is you can ask, okay, what bit is actually added by the network compared to what is captured by traditional statistics? So these information summaries, for example, you can show that they can be trained to, rather than asking them what is the most informative, what are a set of numbers, you can ask what set of numbers gives you the most additional information compared to some already established statistic. You can ask, and so you can sort of split the information into things that you understand and things that you don't understand. Now, maybe you're surprised that I didn't say, oh, but there are ways, there are all these ways of doing sensitivity analysis and response maps and so forth. So there's a set of techniques in the artificial intelligence image processing world for trying to understand what networks are doing. But at least at this point, my impression is that those techniques are still really in the early stages. So they're not really the general answer to the question, what exactly is the network using? There's also an interesting philosophical question that emerges from this, which is that if we ask neural networks to have superhuman performance on certain tasks, then there is maybe a certain tension with the networks being able to explain that to us at a general level, right? If we want to be able to understand what the network does, but then we actually also ask it to do something that humans are not able to do, there's a certain tension there. Maybe it's possible to explain it, maybe not. We were just talking about chess, where we have the situation. We have chess, neural networks playing chess in ways that no human has imagined before. There's now a whole bunch of chess masters trying to figure out why the network is playing this way, and is trying to learn new tricks from the network. So I guess we'll be in a similar situation.
Okay. So I think that if there are no further questions, we can thank Professor Wandelt again. Thank you very much. Thank you. See you.